For all the time that we've been talking about EMR so far in this unit, from the very first day, we've said that EMR is a wave. In fact, we identified 4 properties of waves that were exhibited by EMR that provided evidence for the wave nature of EMR. Remember refraction, we had diffraction, interference. We've been talking about these 2 over the last couple of days, right? And then the 4th one, polarization. All of these things provide evidence for the wave nature of light. And we're not going to throw those away now. We're not going to start saying that that stuff was wrong. But today, we are going to start talking about another aspect of light, another aspect of EMR, called photon theory or particle theory. Now we're saying that light is a wave, as it was before, it still is, but it's also a particle. Sometimes EMR exhibits a wave nature, and sometimes it exhibits a particle nature. I'll give you a little analogy here, okay? I am a father. Okay, I'm also a brother, among other things. I have, in the context of what I just said, being a father and a brother, I have a dual nature. Sometimes I behave as a father, and sometimes I behave as a brother. And my properties differ depending upon what role I'm playing, a father or a brother. I have a dual nature, almost a dual reality. Well, we're now saying that EMR is kind of like that. There is a dual nature associated with it, a duality associated with it. We call it a wave-particle duality. EMR is a wave. It's exhibited by refraction, diffraction, interference, polarization. But it's also a particle called a photon. A photon, we think of it as a particle of light. That's really what it is. It's a little chunk of light, a little particle of light. Like if you throw a bunch of pebbles, each of those pebbles would be analogous to a photon of light, a little particle of light. But the actual definition for a photon is a quantum of energy, a little bundle of energy. So we're saying that each of those little rocks, each of those little pebbles that we're throwing, have a certain amount of kinetic energy associated with them. They're each a little bundle of energy, as this photon is a bundle or a quantum of energy. Now, just like the rocks have an energy associated with them equal to 1/2 mv squared, the kinetic energy of these rocks, these photons have an energy associated with them as well. Einstein said that the energy of a photon, the energy of a particle of light or a quantum of energy, is equal to h times f, or hc over lambda. This equation in itself tells us something about the wave-particle duality associated with EMR. E equals hf, or E equals hc over lambda, is the energy of a photon, the energy of a particle of light. But each of those equations use wave properties, the frequency of the EMR, the wavelength of the EMR. We're talking about the energy of a particle that is found by using the frequency or the wavelength of a wave. So whenever anybody says Einstein comes along and does away with the wave theory of EMR, no, he doesn't. He doesn't do away with the wave theory of EMR at all. He adds to the wave theory of EMR. I was a brother for 31 years before I was a father. And then we came along and added that aspect, that duality. C is the speed of light, yes. I'll tell you what H means in a few moments here. So the energy of a photon, the energy of a quantum of EMR, the energy of a particle of light is related to its wave properties. This E, by the way, does stand for the energy of a photon. And it can be measured in joules, or there's another set of energy that we used a couple of units ago. We just kind of briefly alluded to it a couple times. Anybody remember what it is? Yeah, EV, electron volts. It can be measured in joules or electron volts. What's this value of H? Well, this is actually a constant that we call Planck's constant, P-L-A-N-C-K-S. Planck's constant. This is named after a guy named Max Planck, German guy, who was a founder of quantum theory, which kind of developed into photon theory. Einstein's ideas here weren't completely original. He borrowed upon Max Planck's quantum theory. He just applied it to electromagnetic radiation, applied it to photons, particle theory of EMR. But when you're one of the founders of quantum theory, sometimes you get something named after you. In this case, Max Planck got a constant named after him. The value of Planck's constant is 6.63 times 10 to the negative 34 joule seconds. But it can also be 4.14 times 10 to the negative 15 electron volt seconds. How can you have two different values of one constant? They both mean the same thing. Exactly. They're just two different units, right? What's the speed limit on the highway that comes into Okotoks here? 100 kilometers per hour. Well, you could also say it was 62 miles per hour, or you could also say it was 27.8 meters per second. All those things mean the same thing, right? Just different units. These mean the same thing as well, just different units. Which one do we use? Well, use whichever one's convenient. If you want to find your answer in joules, then you're probably going to use, then you will use 6.63 times 10 to the negative 34 joule seconds. If you want to find an answer in electron volts, then let's use the 4.14 value. Most times you solve a problem involving Planck's constant, most times you can use whichever one's convenient. Like if the answer asks you for the energy in joules, then use 6.63. If it asks for the energy in electron volts, then use the 4.14. Use whichever one's convenient. Most times, 90% of the time, you can use whichever one you want, as long as you're consistent with your problem. There is the odd time, and we'll encounter that over the coming days, where you have to use joules. There is never a time when you must use electron volts. Usually, you do whatever you want. But there is the odd time when you must use joules. So I'll tell you when those situations arise over the next couple of days. But if it confuses you at all, remember this over the next few days. If it confuses you at all, which unit to use, joules or electron volts? Oh man, am I allowed to use electron volts in this question or not? I don't remember, I'm mixed up. What should you do? Just use joules. Joules always work. The reason we sometimes don't use joules is because sometimes it's a little less work to use electron volts. Saves us a unit conversion or two, but it always works. Sometimes a little bit more work, that's all. If in doubt, use joules. If in doubt, use joules. You just have to be consistent through the whole question. That's all. All right, take a look at a couple examples here. First one. Says determine the energy of a photon that has a frequency of 5 times 10 to the 14 hertz. This one's easy. Determine the energy of this photon. That's our frequency. We're just going to say E is equal to H times F. What value of Planck's constant do you want to use? Well, you know what? It doesn't really matter here because you weren't told what unit to put your final answer for energy in. If it said, what's the energy in electron volts? What's the energy in joules? Well, then you'd probably pay a little bit more attention to which value of Planck's constant you use. Because joules always works, I'm going to use that one. I could have used either one in this equation, but I'm just going to decide to go with joules here. 6.63 times 10 to the negative 34 times 5.0 times 10 to the 14 hertz. That gives us a value of 3.3 times 10 to the negative 19 joules. Had you used the 4.14 value, you would have gotten an energy that would have been correct, but it would have been in electron volts rather than joules. And that would have been fine in this question. If the question said, express your answer in electron volts, then you've got two options. You can use the 4.14 value and get the answer in electron volts, or you can do it in joules, because remember, joules always works, and then just convert it. Remember back from our couple units ago, we said 1 EV is 1.6 times 10 to the minus 19 joules. Therefore, X EV is 3.3 times 10 to the minus 19 joules. Solve for X. It works out to be 2.1. If you had have used the first equation, E equals HF, with the 4.14 value of Planck's constant, guess what you would have gotten? 2.1. So in this case, joules was fine. You could have left it at 3.3 as the final answer because it didn't specify. But if it did specify joules, then do what we did. If it specified EVs, then either switch the value of Planck's constant or stick with joules and then convert when you get to the end. One more example. It says how many photons of this frequency would it take to attain a total EMR energy of this energy? That's a lot of energy, by the way, 10 to the 22 joules. It's going to be a big number of photons because that's a lot of energy. We did something like this once before in Physics 30. We weren't solving for the number of photons, though. We were solving for the number of the electrons, yes. How do we do that? Do you remember, Mateo? Yeah, yes, we did. We had to divide something, yes. The analogy I gave you when we studied that, looked for the number of electrons, I said, you got a bag of oranges, has a certain mass. The mass of one orange is this mass. How do you find the number of oranges in the bag? You divide the total mass by the mass of one orange. How do you find the number of the electrons? Total charge divided by the charge of one electron. How do you find the number of photons? It's always total something. Well, what do you have here? Total energy divided by the energy of one photon. So that total energy is 2.5 times 10 to the 22. And the energy of one photon, do we know what that is? No, we could find it. And what's the energy of a photon equal to? Good job, Ben. E is equal to H times F. Since we have a total energy in joules, let's use Planck's constant in joules. Multiplied by the frequency of 1 times 10 to the 16. That gives me an energy of a single photon of 6.63 times 10 to the negative, what is it? 18? 10 to the negative 18. Which we turn around and sub back into here. So the energy total divided by the energy of one photon, we do the division there, we get 3.8 times 10 to the 39 photons. No units. Mateo, how many fingers do you have? Okay, 5. If I said how many fingers on your left hand, you said 5. You didn't say 5 kilograms or 5. But it was no units, right? It was a number. It was how many fingers do you have? 5 or 10 if you're counting both hands. No, those aren't units. Like that can provide clarification or description, but it's not units. If I said how many photons do I have here, I could say 3.8 times 10 to the 39 photons. But if the question is how many do you have, it's also acceptable just to say 3.8 times 10 to the 39, just a number, because the units cancel, right? Joules over joules cancel to give me no units. I'd like you to take a look at worksheet number 20, questions 1 and 2 only now, please.